Hello everyone, I am Pooja Madiwal, student of KLE Society's College of Education, Ankola. In this video, I am going to talk about a very interesting chapter, work and energy. It includes concept of work, scientific conception of work, work done by a constant force, energy, forms of energy, law of conservation of energy, rate of doing work, and the last one is commercial unit of energy. So, what is work? There is a difference in the way we use the term work in day to day life and the way we use it in science, right? To make this point clear, let us understand a few examples, okay? For example, you climb up the steps of a staircase and reach the second floor of a building just to see the landscape from there. You may even climb up a tall tree. If we apply the scientific definition, these activities involve a lot of work, right? In day to day life, we consider any useful physical or mental labor as a work. Activities like playing in a field, talking with friends, watching a movie, attending a function are sometimes not considered to be a work. What constitutes work depends on the way we define it. We use and define the term work differently in science, right? To understand this, let us go for a next concept, that is the scientific conception of work. To understand the way we view work and define work from the point of view of science, let us consider some situations, okay? For example, in the first situation, a girl pulls a trolley and the trolley moves through a distance. Here, the girl has exerted a force on the trolley and it is displaced. Therefore, here work is done. In the second situation, lift a book through a height. To do this, you must apply a force, right? Yes, the book rises up. There is a force applied on the book and the book has moved. Hence, here also the work is done. Now look at the above situations. What it reveals? It reveals that two conditions need to be satisfied for work to be done, right? Which are they? The first condition is a force should act on an object. And the second condition is the object must be displaced. If any one of the above conditions does not exist, work is not done. This is the way we view work in science. And then comes work done by a constant force. How is work defined in science? To understand this, we shall first consider the case when the force is acting in the direction of displacement, okay? Now look at the figure. Let a constant force F act on an object. Let the object be displaced through a distance S in the direction of the force. Let W be the work done. Now, how can we define work here? The work is equal to the product of force and displacement. That is, work done is equal to force into displacement, which is W equals to F into S. If F equals to 1 Newton and S equals to 1 meter, then what is the work done? The work done by the force will be 1 Newton meter, right? Here the unit of work is Newton meter or joule. Thus 1 joule is the amount of work done by an object when a force of 1 Newton displaces it by 1 meter along the line of action of the force. To understand this concept, let's solve one example, okay? For example, a potter lifts a luggage of 15 kg from the ground and puts it on his head 1.5 meter above the ground. Calculate the work done by him on the luggage. Here, mass of the luggage M is equal to what? 15 kg. And displacement S is 1.5 meter, right? Yes. The work done is given by what? W equals to F into S, which is equals to mg into S. It is 15 kg into 10 meter per second square into 1.5 meter, which is equals to 225 kg meter per second square. It is 225 Newton meter or 225 joule. Therefore, the work done is 225 joule. And then comes energy. What is energy? Have you ever think life without energy? No, you can't, because life is impossible without energy. Where do we get energy from? The sun is the biggest natural source of energy to us, right? Yes, the sun is the source of energy. Many of our energy sources are derived from the sun. We can also get energy from the different sources. For example, nuclei of atoms, the interior of the earth, and the tides are all sources of energy. The word energy is very often used in our daily life, right? But in science, we give it a definite meaning. Let us consider one example, okay? Look at the pictures. When a balloon is filled with air and we press it, we notice a change in its shape, right? As long as we press it gently, it can come back to its original shape when the source is withdrawn. However, if we press the balloon hard, it can even explode, producing a blasting sound, right? Yes. In this example, what can we observe? Here, the balloon means the object acquires through different means the capability of doing work. So, what it concludes? It concludes that an object having a capability to do work is said to possess energy. Then, what is energy? Energy is defined as an object having a capability to do work. The energy possessed by an object is thus measured in terms of its capacity of doing work, right? Yes. Then, what is the unit of energy? The unit of energy is therefore the same as that of work, that is joule, which is denoted by capital J. 1 joule is the energy required to do 1 joule of work. Sometimes a larger unit of energy called kilojoule is also used. 1 kilojoule is equals to what? 1 kilojoule is equals to 1000 joule. And then comes forms of energy. Luckily, the world we live in provides energy in many different forms, right? Yes. Then, what are the various forms of energy? Various forms of energies are mechanical energy, in that potential energy and kinetic energy, heat energy, chemical energy, electrical energy, and light energy. But in this chapter, we are going to study more about potential energy and kinetic energy, okay? And the first one is kinetic energy. What is kinetic energy? Try to recall. Objects in motion possesses energy called kinetic energy. For example, a falling coconut, a flying aircraft, a flowing water, a running athlete are all possesses which energy? Yes, kinetic energy. In short, we can define kinetic energy as the energy possessed by an object due to its motion is called kinetic energy. The kinetic energy of an object increases with its speed. And the expression for kinetic energy is given by Ek equals to half mv square. Here m is the mass and v is the uniform velocity. Let's understand this topic by solving one example, okay? For example, an object of mass 15 kg is moving with a uniform velocity of 4 meter per second. What is the kinetic energy possessed by the object? Here Mass of the object m is 15 kg, right? Yes. The velocity of the object v is what? 4 meter per second. Then what is the expression for kinetic energy? Yes, the expression for kinetic energy is Ek equals to half mv square. By substituting given values, what we get? We get half into 15 kg into 4 meter per second into 4 meter per second, which is equals to 120 joule. Therefore, the kinetic energy of the object is what? The kinetic energy of the object is 120 joule. And the second one is potential energy. Let's understand this topic by doing one activity. Okay? For example, take a rubber band. Hold it at one end and pull from the other. What happens? Yes, the band stretches. And then release the band at one of the ends. And what happens? Yes, the band will tend to regain its original length. Obviously, the band had acquired energy in its stretched position. Here, you transfer energy when you stretch a rubber band. The energy transferred to the band is its potential energy. The potential energy possessed by the object is the energy present in it by virtue of its position or configuration. Let's go for one more activity, okay? Take a bamboo stick and make a bow as shown in picture. Place an arrow made of light stick on it with one end and supported by the stretched string. Now stretch the string and release the arrow. Here you can notice that the arrow flying off the bow, and also notice the change in the shape of the bow. The potential energy stored in the bow due to the change of shape is thus used in the form of kinetic energy in throwing of the arrow. To understand this concept clearly, let's solve one problem, okay? For example, find the energy possessed by an object of mass 10 kg when it is at a height of 6 meter above the ground. Given g equals to 9.8 meter per second. Here mass of the object m is 10 kg, displacement means height h is 6 meter and acceleration due to gravity g is 9.8 meter per second. And then potential energy equals to mgh, which is equals to 10 kg into 9.8 meter per second into 6 meter, which is equals to 588 joule. Therefore, the potential energy is 588 joule. And the next concept is law of conservation of energy. According to this law, energy can only be converted from one form to another. It can neither be created or destroyed. The total energy before and after the transformation remains the same. The law of conservation of energy is valid in all situations and for all kinds of transformations. And then comes rate of doing work. Do all of us work at the same rate? No. A stronger person may do certain work in relatively less time. A more powerful vehicle would complete a journey in a shorter time than a less powerful one. Yes, here we talk about the power. Exactly, the power measures the speed of work done. That is how fast or slow work is done. We can define power as the rate of doing work or the rate of transfer of energy. If an agent does a work W in time T, then power is given by work by time or P equals to W by T. The unit of power is watt. And we express larger rates of energy transfer in kilowatts. That is 1 kilowatt equals to 1000 watts or 1 kW equals to 1000 joule per second. For example, a boy of mass 50 kg runs up a staircase of 45 steps in 9 seconds. If the height of each step is 15 cm, find his power. Take g equals to 10 meter per second. Here weight of the boy, that is mg equals to 50 kg into 10 meter per second, which is equals to 500 Newton. And height of the staircase, that is h equals to 45 into 15 by 100 meter, which is equals to 6.75 meter. Time taken to climb, that is t equals to 9 seconds. Therefore, the power equals to work done by time taken, which is equals to mgh by t. That is 500 n into 6.75 meter divided by 9 seconds, which is equals to 375 watt. Therefore, the power is 375 watt. And the last concept is commercial unit of energy. The unit joule is too small and hence is inconvenient to express large quantities of energy, right? Yes. So we use a bigger unit of energy called kilowatt hour. Then what is 1 kilowatt hour? 1 kilowatt hour is the energy used in 1 hour at the rate of 1000 joule per second.